Welcome, my name is Camille, and today we're going to tackle every single possible limit problem you'll ever see on any exam. Of course, at most, I assume you're AP Calc students because this is the theme of my YouTube channel, but maybe you can be just a Calc student, whatever. You will need this video. This is the only video you need in order to be a G in limits. We'll just literally take and break down every single limit you'll ever see. So, let's start. It's going to be super practical lesson. Of course, we'll also add theory in addition to the problem. We'll look at the problem, identify the fact that actually, we're missing out. We need some more theory. I'll add theory as a bonus, right? So we'll go this way. Problem theory, problem theory, problem theory, problem theory, and this way, I believe you'll be able to actually understand and never ever have any questions in terms of limits in future. So let's start. Number one. And before we dive in, of course, we need to give some theory a bit. Let's make sure that you know at least some basics, right? I assume you know some basics, but maybe you don't. First of all, let's discuss some really important things. So when we write limit as x approaches c of f of x equals L, we basically say that as x approaches c, the values of our function, right? We have a function. The values of our function heads toward this number, real fine number L. So this is what it means. And we also know, and now this is a small introduction to limits. We also know about one-sided limits, and I want to now say about one-sided limits from the beginning because, I genuinely believe it's very, very clear idea. Let me remove this first. So, because when you think about it, what does it mean x approaches c? What's that? X approaches c. When you think about it, x approaches c, what's that? The values for a function approach some number L. It's kind of strange. It's kind of weird. But if you talk about one-sided limits, it's pretty intuitive, clear thing. Because, okay, let's imagine this is our function f of x. And this is point C. So it's here. And when we say x approaches c, what does it even mean? But if I say, let's look at the limit, one-sided limit, left-hand limit. Yeah? Let's say, what happens, I wanna look at the number, the values of our function approach as we come closer from the left, right? This is kind of logical. Wanna evaluate this limit as x approaches c from the left of f of x. I want to know what's the value, what's the number, the values of our function approach. And that's really clear because we think, okay, I want to come closer to c from the left. I want to see how my function behaves itself, right? What happens there? So as we approach c from the left, as we come closer from the left, I see that the values for a function heads toward number L, which is f of c in fact here, but let's say it's some number L, right? So this is L. It's number L. I guess it's clear, right? When we talk about one-sided limits, it's really clear. From the left, we approach L. Sure. From the right, the same thing from the right. We can say, all right, from the right, as we come closer from the right, we come closer to c from the right, we try to look at the behavior of the function, and we see that, we also approach the same number L. And this is really clear, I hope. And in this situation, only in these scenarios, if and only if your one-sided limits are equal to each other, your general limit exists. So this thing exists only if left-hand limit from the left and from the right you approach the same value. So this way you can intuitively understand at least when your limit exists. Because it's kind of easy to understand, all right, what is the value, what is the number of values or function approach from the left? You come closer from the left, boom. You see, all right, I approach L. From the right, again, you go from the right, you see that you also approach L. One-sided limits are equal, then the general limit exists and equal to L. Okay, this is the basics. And here, L, also by the word, this is f of c. And it's not a coincidence, as you know. I hope you know that. I hope you know that. In very, very, very often, in fact, we can evaluate the limit as just evaluating our function at point C. So you have a limit. Imagine you have a limit here. Again, we have a function f of x as x over c. Want to find L. Want to find the number. Want to see what is the number we approach. The values for function approach has to work. Want to find that number, and very often we can write down that's just that it's going to be f of c. So we can just take c, substitute in our function, and this is going to be the answer. But of course, it works only for continuous function. And for the people for the students who still don't know what's continuity. When we say the function is continuous, in simple words, it just means graphically that you can sketch the graph without lifting up your pen, pencil, whatever. So in this case, absolutely, I sketch it without lifting up my pencil. This is continuous. This is continuous. Let's better show not continuous functions. Right, this is, here we have discontinuity, which is hole. Right, when you have a hole, breaks, again, I'm lifting up my pen to sketch it. I have some jumps, holes, breaks, asymptotes. This is not some uniform, let's say, a uniform line. I need to lift up my pen in order to sketch the graph. So this way, it's like simple definition. I can say this definition is some tip, how to define the continuity of your function. So if your function is continuous, it means what? It means that you can evaluate the limit by just substituting the number into your function. That's all. So this way you can find the limit. All right, and this way, and basically, as we know, most of the functions you work with, polynomials, logarithmic functions, trigonometric functions, all that functions, logarithmic, exponential functions, all that functions, they are all continuous, of course, everywhere except for the points where not defined. So if you take the function, basic function, elementary function, they call elementary functions, and you find the point where it's not where it's defined, then it means that it's going to be continuous. And it just means that usually when you see a limit problem, first of all, do the direct substitution anyway. You take the number every time. So let's start with the first one. Let's just move on. Right, stop talking and move on, finally. So this is some tip. What happens? Oh, sorry. So remember, anyway, regardless of your limit, you need to take your limit and substitute 3 here, not 3c, generally c. So write down the limit, and the first thing we do, direct substitution anyway, because to check this continuity or something, it's kind of, what's the point? Let's just substitute. If it works, then absolutely your function is continuous, and probably this is your answer. This is the final answer. If it gives you 0 over 0, which happens quite often, so we substitute 3, we get 9 minus 9 divided by 3 minus 3, and we get 0 over 0. And this is kind of, let me tell you one secret fact that's going to happen in 99% of scenarios, especially in your exams. It's very rarely you take the number, you substitute it there, and you get the final answer. It's very rarely happens this way. And this is all what this video about. Basically, we'll just discuss the tricks and methods and tips how to overcome this situation. Because every first step, you will be always direct substitution anyway. Even if it's not gonna work out every single time, we'll do it anyway. So we get 0 over 0. All right. So let's move to the first trick method. And first one is just some algebra. It's very simple. You try to cancel out something. You need to look at the fraction, function, whatsoever, expression. You need to look at that and try to identify some ways to cancel out something. Factor, cancel out, do something. You need to do some algebra in order to simplify your expression. and then try the substitution again, because we'll return back to that every single time. Here we get 0 over 0. It doesn't work. Sheesh. So we take the limit again, and we try to do something. And we see here, it's very simple, of course, but we can factor the numerator. It will be x minus 3 multiplied by x plus 3 divided by x minus 3. We cancel out x minus 3. Wonderful. And we get that limit. It's equal to a limit as x equals 3 of x plus 3. And now we substitute 3 and we get 6. So this is going to be the final answer. That simple. Again, we start with the substitution. It doesn't work. Next, I will, of course, now learn a bunch of different ways. But first method is to look at the algebra and try to simplify. Here it's very simple. We factor, cancel out, and it works. Next. Ah, beautiful tea. All right, number 2. And here, okay, I will actually show you both methods every time, because in such problems, usually, in fact, in every problem where you get 0 over 0, which is indeterminate form, you can use L'Hopital's rule. It's some kind of ultimate weapon against all the indeterminate forms. Let's write it down. Yeah, so every time when you see we have something like that, you have f of x divided by g of x, you have some fraction, and as x approaches c, some number c, and you get indeterminate form. On AP Calc exam, it's just 0 over 0 or infinity or infinity. So you get these or these. You get one of these indeterminate forms. If you actually study some more complicated calculus course, you will also have multiple other indeterminate forms, but I'm not going to touch them today, because anyway, we're based on AP Calc here. We're focused on AP Calc. Alright, so if you see one of those, 0 over 0 or infinity, it means, in this case, you can use L'Hopital's rule, and it says that. So you substitute c, you get 0 over 0 or infinity. Then in this case, you can, as a next step, say that, okay, then this limit is equal to the limit as x approaches c of f prime of x divided by g prime of x. So here you say, okay, let me substitute c. Let me do first step. I substitute c, I get 0 over 0 or infinity, some indeterminate form. See, what do I do now? And then you'll remember the L'Hopital's rule, and it says that, don't worry, man, don't worry. Man, woman, of course, I assume, no. Sorry, lady, gentlemen, don't worry. It says, you can just take derivatives separately. You take f of x, you take derivative. You take g, take derivative. And you get f prime of x divided by g prime of x. Right, divide them. You divide f prime of x by g prime of x. And you try to evaluate this limit again. And you can do it multiple times. Imagine you did it. You took derivatives. You substitute c now again. And it doesn't work again. Imagine it gives you 0 over 0 one more time. Or infinity. So again, some indeterminate form. What do you do next? You take derivatives one more time. You can continue that to eternity. Until you get to a moment where it works. You can do it. You can apply 2, 3, 4, 5, 6 times till it works. Of course, sometimes it's not the fastest way, but it's as we said, this is something that works for 100%. You just have to heat, and at some moment of time you'll hit the wall. All right. So let's apply it here. And of course, the second method here is to know basic trigonometric limit. But let's first solve it with L'Hopital's rule. Let's remove that. All right, we write down the limit. Sine of 5 of x divided by x. We substitute 0. First step, as usual. We substitute 0, we get 0 over 0. What happens now? We know, we identify this is indeterminate form. Fine. When you have indeterminate form, 0 over 0, infinity or infinity, you can use L'Hopital's rule every single time. You don't care. So let's try to use it. We take the function. We know this is f of x, this is g of x. So we take the derivatives separately. This is extremely important. Don't try to apply the quotient rule here. This is a mistake. You take f prime of x, you take g prime of x separately. And then you say that, okay, that's equal to limit as x approaches 0. So what's f prime of x? That's 5 cosine of 5 of x. The chain rule. I hope you know that. If you don't know that still, if you wanna derivatives broken down, basically just tell me. Write that in the comments and we'll tackle all the derivatives too. 5 multiplied by cosine of 5 of x. Cosine of 5x. 5 of x. 5 multiplied by cosine of 5x. Absolutely. And then we take the derivative of g of x. So we take, yeah. And we get 1. So that's going to be 5 multiplied by cosine of 5x divided by 1. Alright. So we substitute again. This is L'Hopital's rule, right? We applied L'Hopital's rule. Now we substitute 0. We get 5 multiplied by cosine of 0 divided by 1. What's cosine of 0? That's 1. So now it works just fine. It's equal to 5 multiplied by 1 divided by 1, which is 5. This is the final answer. 5. So L'Hopital's rule actually here is a shortcut. The second way, another way to tackle this problem is to know the basic trigonometric limit. And I can't say that it's kind of easier because you have to actually remember something. But in case you do, it works just fine too. So the basic trigonometric limit says that if you have a function sine of x divided by x as x approaches 0, and that's this limit, you take the limit as x approaches 0, this is going to be equal to 1. This is the basic trigonometric limit. It's actually derived from the Squeeze Theorem. We're going to discuss the Squeeze Theorem today too. And that gives us what? Oh, and here we can just work with our limit a bit. We have sine of 5 of x divided sine of 5x divided by x. And what do? We see that, oh, we don't have 5 in the denominator. But it's fine. Multiply by 5, divide by 5, and you'll have 5 in the denominator. What's the problem? We can always multiply by 1. Basically, we multiply by 1, so nothing changes. Now we write 5 here, and we pull this constant out to front. So we will get 5 multiplied by limit as x approaches 0 of sine of 5x divided by 5x. That's all. And now we identify the basic trigonometric limit, which is equal to 1. And we get 5 multiplied by 1, which is 5. So it works too. But my advice, of course, I mean, numerization is good, but L'Hopital's rule is better in this case. Alright, number 3. Let f be the function defined as shown. So we have some piecewise function. 2x plus 1, 5, 3x minus 1. What the value of the limit is this. So we want to find the limit as x approaches 2. And every time when you have a piecewise function, the first thing you should do, you have to ask yourself a question. Is it exist? Does it exist? Right? Does it exist? Because when you have a piecewise function, there is a huge probability that you're going to have some hole or jump or something like that. I'm not sure that we're going to have some jump. Or maybe I'm not right. I don't know. Let's see. We want to look, first of all, at the limit from the left of our function, and want to look at the limit from the right of our function. And from the left, it means that x is less than 2. So we need to use this function. So it's going to be limit as x approaches 2 from the left of 2x plus 1. We need to evaluate this limit. And then we also need to look at the right hand limit. Right? We need to look at so we need to take the values higher than 2, greater than 2. That's going to be 3x minus 1. So we have to take the function 3x minus 1. All right. We operate from the left and from the right. We write down the limits, and then now we look at the function. What is going on here? Of course, we can just tackle these limits by substituting 2. We get 5, and here we get also 5. So the left-hand limit is equal to 5, the right-hand limit is equal to 5. Their one-side limits are equal to each other. It means the general limit exists, and it's equal to 5, too. So the final answer is A. That's why, yeah, it exists and it's equal to 5. Next. That's it was kind of not super interesting, because usually it will give you some problem where it won't work. It will just give you the problem where the substitute left-hand limit is not equal to the right-hand limit. It means that general limit doesn't exist, and you'll write that it's going to be non-existent. But here, okay, it exists, it's 5. Also cool. Number 4. So this is where we need to apply the rational theorem. In fact, there are a bunch of different ways to tackle this problem. Really lots of different ways. This is about, let's give some small theory. Because look at the limit right now. And when you have a limit as x approaches infinity, and you have a rational function, so we have some two polynomials here. M of x, n of x. So we have two polynomials. Exactly what happens here. X approaches infinity, we have two polynomials. What do we do here? And basically we can tackle this problem again in a couple of ways. First of all, you may remember the rational theorem. There's a name, but basically most people just remember that, yeah, if the degree, right, if the degree of the polynomial in the numerator is higher than the degree of the polynomial in the denominator, right, if m is greater than n, then it's going to be what? It's going to be infinity. If it's equal to n, then it's going to be the ratio of their leading coefficients. If it's less than 1, if it's less than n, it's going to be 0. This is one of the ways to look at that. Now, or, I mean, degree, what's degree? You just have to, let's look at our problem. You have to look at the expression. What's the degree of the polynomial at the top? That's 3. It means you just have to look at the numerator first, identify the x with the highest exponent. Here it's 3, so x cubed. So highest x with the degree here is 3. You say, okay, so here's degree is 3. Here, the same thing, basically. We need to, then you move to the denominator, you need to identify the x with the highest exponent again. You see that it's 3 one more time. So you have 3 and 3. So it's this situation. Then it's going to be just the ratio of the leading coefficients. So 4, you need to divide 4 by 5. So the final answer will be 4 over 5. This is it. But, you know, the question is, how do we get that? I mean, of course, you can easily remember the theorem, but at least let me say how to easily remember the theorem. Yeah, how to think about it, how to remember the theorem really in a real simple way. Why this is logical? Because just think about it. Look at the expression at the top. Let's work with that first. 4x cubed minus 2x squared plus 1. This is just how I think in my head. Because usually, when I look at the limit, as x approaches infinity, I look at the expression. I see, for example, 4x cubed minus 2x squared plus 1. And I say, okay, this is approximately, this is how I think. I write down the limit. Okay, let's move just somewhere here. I write down the limit. And I say, okay, this is approximately, let's write down again. I think, okay, 4x cubed is much bigger, much greater than 2x squared and especially 1 as x approaches infinity. Just think about it, we approach infinity. Of course, there's going to be nothing in comparison with 4x cubed. So I'll just keep 4x cubed. I will say it's approximately the limit as x approaches infinity 4x cubed divide by, and here I'll just keep 5x cubed because I'll say, yeah, 5x cubed is much greater than 3x. This is absolutely nothing as x approaches infinity. And here's why. Let's let's just substitute numbers and you will see why it's true. So this is our expression. Let's say that x equals 10. It will be 4 multiplied by 10 to the third minus 2, 10 squared plus 1. So it's, let's better even, let's do it this way. Let's just write down without scientific notation. Let's say it's going to be 4 grands plus 200 plus 1. Imagine you substitute now 100. You'll get it. Look at that. Basically 4,000, 200, 1, nothing. Then we substitute 100. We get we get 4 millions. Yes or not? Yes. We get 4 millions plus 2. I guess we get 20 grands. Yeah. We get 20 grands plus 1. Again, 4 mil. 20 grands plus 1. And this difference will only grow as x approaches infinity. This is x equals 100. Imagine we now take, x equals million. What happens there? It's really scary even to imagine what happens there. So as x approaches infinity, the difference will be so huge that you can say, all right, I don't care about 2x squared plus 1. This is the most important thing here. This is the most important term in our expression. I'll say, okay, so approximately I'll say this limit is equal to the limit as x approaches infinity. This is how I think. Of course, you shouldn't write it down, but this is just how you can think. 4x cubed divided by 4, 5x cubed. And the same thing in the denominator, right? You look at the denominator, you say, for as x approaches infinity, this is going to be much greater than 3x. There will be so huge difference, I can just forget about 3x. It doesn't change a thing here. So you say this approximately is equal to this. And then, you say, okay, and now I can cancel out x cubed. I'll get 4 divided by 5. This is just, basically, you will get the same answer as if you remember the rational theorem, right? If you remember. But this is just, it's kind of the same thing. This is just how it's easy to remember and, make sure that you remember right. Because sometimes you can somehow misinterpret and you can say that, okay, the degree in the denominator is higher, then it's going to be on 0. But it's not true, it's going to be infinity. So you can check yourself this way too. You can do it in your head. It's very fast. You look at the expression, you say, okay, this is 4x cubed. It's much bigger than, much greater than anything else. As x approaches infinity, the same thing with the denominator. You say, okay, this is much greater than anything else. So we'll get 4 over 5. Okay. And of course, imagine now there was 4 here. Then you would get 4x cubed divided by 5x to the 4th. You would cancel out x cubed and we get 4. So imagine there was a 4, you would cancel out x cubed and you get 4 divided by 5x. As x approaches infinity, you'll get 0. Right? Because you have some super huge number in the denominator is some 4. Of course, you will get 0. So this is just another way to remember the rational theorem. And check yourself if you just forgot. But basically, right, you just look at the limit. You have to identify the highest. You have to identify x with the highest exponent in the numerator. It's 3. In the denominator, it's also 3. Let's remove 4. Right, and you say, okay, now it's going to be the ratio of the leading coefficients. It's going to be 4 over 5. This is the final answer. And there's also the third method, but let me show it in the. I'm sure we'll see one more limit of the sort, so we'll return back to the third method there, because as I told you, there are plenty of different ways to tackle the problem. Number 5. Let's write it down. I'm already tired, you know. I didn't want to explain in so more many details. You know, I didn't want to do that. But now I'm just sitting and talking and talking. What's the time now? Let me take a small break. All right. After a small break, I'm back, and we can continue our conversation. So this is our limit. What do we do first? The ref substitution, as usual, of course. We substitute 0, and we get 4, square root of 4, which is 2. 2 minus 2. Okay, let's write it down this way. What's happening? Oh, sorry. Square root of 4 minus 2 divided by 0. Which is going to be 0 over 0 again. One more time. 0 over 0. And it means that we need to do something else. Of course, we can apply L'Hopital's rule here, but it's kinda, I don't know, we can do it. Or also a different way. You can apply the L'Hopital's rule, you can do it on your own. Yeah, pause the video, apply the L'Hopital's rule and find the answer. I will show you another method here. We can easily remove the radical from the top by multiplying by the conjugate and divide by conjugate. Again, we will multiply by 1, so nothing changes. But it will change the entire situation here as we remove the radical from the numerator. We're gonna get limit as x approaches 0 of x plus 4 minus 4 divided by square root of x plus 4 plus 2. Great. And now 4 cancels out, right? And we get that limit as x approaches 0 of x divided by square root of x plus 4 plus 2. And yeah, we can substitute 0 now, and we'll get that you get 0 divided by what? 4. So you get 0. The final answer is 0. Final answer is A. But you can obtain the same answer basically by applying the L'Hopital's rule. You'll get the same answer, but I'm just giving you another way. So it's again some algebra trick. But here, instead of just factoring, sometimes when you have a radical, you can multiply by conjugate, divide by conjugate. It also gives you the answer, gives you correct answer, which is also important. Or you can apply L'Hopital's rule. L'Hopital's rule is a genuine ultimate weapon, as we discussed previously. We move forward, number 6. What do you do now? Let me write it down first. And as usual, of course, we start with the ref substitution. And I bet it's not gonna work out. I'm almost sure, because I was the man who created the problems. But I substitute 3, I get 0 over, so it's 6, it's 9 minus 6 minus 3, so it's also 0, of course. No doubts. 0 over 0. We can apply the L'Hopital's rule, or we can do some algebra. And here, it's easier to do some algebra because it's easier to factor the denominator. And we know it's gonna be x minus 3, x plus 1. So we cancel out x minus 3, and we get limit as x approaches 3 of 1 over x plus 1. So we substitute 3 now. We do the ref substitution one more time after we canceled out, after we simplify the expression. And now we substitute 3, we get 1/4. So this is the final answer. C. We move forward. Number 7. And this one, yeah, basically here, just imagine you have e to, of course, let's first do the ref substitution. Substitute 0, we get 1 minus 1 divided by 0. So it's going to be 0 over 0. So we need to apply other trick, theorem, maybe L'Hopital's rule. And yeah, let's do L'Hopital's rule, because if we, what are you going to do here? Multiply by conjugate, divide by conjugate? There's no such thing. Do some factoring. Try it out, but I don't see how to do that. The only thing here is to do L'Hopital's rule. This is the best move on the chessboard. So let's apply the L'Hopital's rule. We see this is our f of x, this is g of x. So we take derivatives. F prime of x was gonna be, we apply the chain rule first, so it will be so e to 2x multiplied by 2, right? Derivative of the outside function multiplied derivative of the inside function, which is 2, and minus 0. So it's gonna 2 e to the 2x. And g prime of x is gonna be, so the derivative of x is 1. So substitute this here, we get limit as x approaches 0 of 2 e to the 2x divided by 1. Now if you substitute 0, you will get 2. The final answer is 2. Final answer is C. Right? That very, very simple. We move forward. Basically, L'Hopital's rule is some really genuine ultimate weapon, as we discussed. It's literally changes absolutely everything. Number 8. Here actually nothing will change. Nothing will help. Because we have x squared multiplied cosine of 1 over x. And if we substitute 0, we get 0 multiplied cosine of 1 over 0. Yeah, and you are not able to apply the L'Hopital's rule here. It's some strange stuff. Absolutely strange thing. And here, actually, this is, some different universe. There is direct substitution. After that, we use some tricks. You can do algebra. Yeah, try to multiply by conjugate, divide by conjugate. Maybe factor something, cancel out. Maybe apply the L'Hopital's rule. And there is a different universe, which sometimes you can pull and bring here. Some tool, secret tool. And it's called Squeeze Theorem. And here it's gonna work. And it says, let's just talk about the Squeeze Theorem a bit. It says that if you have a function, 3 functions, g of x, which is less than or equal to f of x, which is less than or equal to h of x. So we have 3 functions. And this inequality holds for all x in some interval, on some interval, right? You take any x and just it works. This is true. Then, if the limit of as x approaches some c of g of x is equal to L, and the limit of function h of x as x approaches, what's important, the same number, right? C, they're both approach c, as x approaches c, h of x approaches L, it means that the limit of f of x is also going to be L as x approaches c. The limit as x approaches c of f of x is going to be L. And it's basically called Squeeze Theorem because graphically, right, if you look graphically, it will be something like, let's say it's going to be g of x will be red, h of x will be green, and here's some f of x. And at that point, this is point C. As you see, it's kind of there. It's like squeezed. F of x is squeezed by these 2 functions, right? H of x and g of x. They squeeze our function f of x at point C, and that's why limit is equal to L. So it's Squeeze Theorem. It kind of refers back to the graphical interpretation. All right. So we are going to use it here. Okay, now let me show you how to do it. Let me show you exactly how to do it. We'll remove that stuff. Again, I hope you remember that. It's in fact, it's very, very easy. I mean, you just need to, now, we have a function f of x. We just need to find, yeah, of course it's easy to say, but we need to find g of x and h of x. And then, so this is the first thing. We need to write down some inequality. We need to find g of x and h of x such that limit of g of x and h of x as x approaches c, here it's 0, right? Because we wanna find this limit. So we wanna find two functions which has the limit as x approaches 0, 0. Not 0. So we want to find some two functions, and the limit of those functions must be some number. We need to find because, and what's important, similar number, right? The same number, and then f of x is going to be that number too. The limit of f of x as x over 0 is going to be that number too. So this is what we want to do. How are we going to find those functions? This is, I guess, the most important question here today. How are we supposed to find those functions? And don't worry. For cosine and sine, it's very easy, because you can always write down this inequality. For cosine, sine, because cosine of 1 over x, or cosine of anything, it's always less than 1 or equal to 1, negative 1, or and greater than negative 1 or equal to 1, and it's less than 1 or equal to 1. Now this is for it works for all x in the domain of our function. It works everywhere. So you can always write down this inequality. And now we can just, how do we get f now, f of x? We just need to multiply by x squared. So we say that it's going to be negative x squared is less than or equal to x squared multiplied by cosine of 1 over x, and it's less than or equal to x squared. That's simple. And now let's take the limits. Let's take the limits as x approaches 0 of negative x squared and x squared and positive x squared, right? Just x squared. And we know that, of course, what's the limit? Substitute 0 and you get the answer. We substitute 0, get 0. Substitute 0, get 0. So they both approach 0 as x approaches 0. So the limit is 0 for both of those functions. So we found g of x, we found h of x. And it means then that we squeezed our function f of x. And it means that the limit of our function f of x as x approaches 0. Yeah, that's all. They need to have the same number here. The same number c. Here is 0. That's going to be also 0. That's all. We squeezed the function. This is the squeeze theorem. So the answer is A. Oh, I hope there will be no theory anymore. Number 9. We need to evaluate this limit. Now I'll speed up. What do we do first? We substitute 0. We get 0 minus 0 over 0. Boom, it's 0 over 0. We need to move on. Alright. 0 over 0. We can apply L'Hopital's rule, and let's do it, because I'm not going to now do some simplification, algebra tricks. No. Let's apply L'Hopital's rule. Straight to the point. So we take the roots of f of x. First, we take f of x. We need to find f prime of f of x. F prime of x. Sorry. We need to find f prime of x. So what do we do? I'm going to be 1 minus cosine of x. Very simple. And we need to find g prime of x. That will be 3x squared. So we get the limit as x approaches 0 of 1 minus cosine of x divided by 3x squared. Now, do the direct substitution again. Substitute 0 again. We take 0 and we plug it in. We get 0, we get 1 minus cosine of 0, which is 1, divided by 0. So it didn't work out. Beautiful example. Because now we'll apply the L'Hopital's rule one more time. We'll just hit and push until we hit the wall, break the wall. We'll continue. Because right now, imagine, again, substitute 0. You get 1 minus cosine of 0, which is 1, divided by 3 multiplied by 0. So you get 0 over 0 one more time. So you need to continue the chain. You need to move forward. So we say, okay, this is equal to the limit as x approaches 0, and we need to take the derivatives now of these functions. We take first f prime of x is going to be, so this is our f now. Yeah, we need to find f prime of x. So that will be 0 minus derivative of cosine of x, that's negative sine of x. So that will be plus sine of x. G prime of x will be 6x. Okay, so we can write it down that it's going to be sine of x divided by 6x. We substitute 0 again, and we get 0 over 0 one more time, unfortunately. And it means that we apply L'Hopital's rule one more time. Okay, we're not sad, right? Because we know eventually we'll end up with some normal answer. It's gonna happen, don't worry. So it will be the third time we use L'Hopital's rule. Now the function f of x is sine of x, so we take f prime of x is gonna be cosine of x. And g here is g of x is 6x, so g prime of x is gonna be 6. So that will be, okay, let's remove that. That will be the limit as x approaches 0 of cosine of x divided by 6. And now if it steps to 0, finally we get 1 over 6. So the answer is B, finally. Yeah, it was kind of hard for a moment, but who cares? Who cares? So, what's the lesson here? Don't be scared. Don't be afraid to use the L'Hopital's rule as you wish. You know, the multiple times, 4, 6, 7. You can use it on 10 times, 100 times. Don't worry. Don't be afraid to do that. At some moment of time, you will get the answer. Of course, only if you get indeterminate forms, right? If you get 0, 0, or infinity, or infinity. Only in this case, you apply L'Hopital's rule. In any other cases, you don't do it. You don't just take some limit and start taking derivatives. It's a weirdo. No. Alright, we look at the number 10. You know, what's the time now? Oh, it's only 70 minutes. Fine. I said that I'm gonna speed up, but I'm still slow. Okay, what do we do now? We substitute infinity and we get infinity divided by infinity. Yeah, we get some indeterminate form one more time. Substitute infinity. And as you see, this is not rational theorem, right? There's no just some expressions at the top and in the denominator. This is not the rational theorem. This is not, you don't have some polynomials. So we need to apply the L'Hopital's rule. Yeah, this is again, the best move here. Or you can multiply by conjugate and start doing something like that. It might work too, actually. But let's lose L'Hopital's rule. It's like basic stuff. Now what do we do? Because yeah, don't actually don't worry that there's negative infinity, right? It's fine. It's just anyway, it's infinity or infinity. So actual sign doesn't really change a thing here. Don't worry. L'Hopital's rule you can apply it. You need 0 over 0 or infinity or infinities. It can be negative infinities, it can be positive infinities. You just need that. And of course we get it here. So we can apply the L'Hopital's rule one more time. We need to take the derivative of 2x minus 3, that will be 2. And we need to divide by the derivative of x squared plus 1. And let's write it down this way, you know. Let's say that's x squared plus 1 to the negative, not negative, to the 1 over 2. So we just need to apply the power rule here and the chain rule too. So it's going to be 1 over 2 multiplied by the x squared plus 1, negative 1 half multiplied by the derivative of the inside, which is 2x. And that's all. That's all. Easy. Yep. And now we can rewrite it as the limit x approaches negative infinity of 2 divided by x multiplied by x squared plus 1 x squared to negative 1 over 2. Okay. Or basically, this just means that, let's write it down this way, that we can move x squared plus 1 to the top. Fine. Now we substitute infinity again, and nothing really changes. You know, it's really kind of sad. Let me actually think about it. Is this the best way? Now, because now we've substituted infinity, I guess you see what happens if you substitute infinity now. We will get again indeterminate form, and we can apply the L'Hopital's rule one more time, of course. But is this the best move? Is this like the fastest way to get the answer? I'm not sure. I'm not sure at all. Unfortunately, I'm not sure. Let me think about it. Maybe multiplying by radical was a really good idea. Maybe that was a good idea. Wait a bit. Okay, let me apply L'Hopital's rule one more time. So we apply it one more time. We get 1 here, and at the top we get 2 multiplied by what? We take the derivative of this thing. So it will be 1 over 2 multiplied by, I don't have enough place. Let me move that here. Two multiplied by 1 over 2 multiplied by, of course, x squared plus 1 to a negative 1 half. No, it's gonna be fine. We're gonna be fine. And multiplied by 2x. So basically, it's equal to limit as x approaches negative infinity of 1 over x squared plus 1 squared. And now if substitute infinity, we will get something big, huge, some infinity. At the bottom, 1 over infinity. What's that? This is if substitute infinity, right, again. You get 1 over infinity, that's 0, of course. Because, again, if you don't know it, if it's actually not clear, take the values, take the numbers. Imagine x is unknown, 100. That's 0.01. If it's 1,000, it's 0.0001. Imagine it's like a million. It's 0.001. You take the, imagine now you take the infinity. It's infinite huge number. Of course you will get, it will be actually something like 0. So we assume that 1 over infinity is 0. Not only 1, any number over infinity is 0. So the answer is C. A. Oh, it's not C. C, 0. We move forward. So what was the amount of attempts here? So we use L'Hopital's rule 1. Oh, basically only 1 time. 2 times. We use it 2 times and we hit the answer. Number 11. Shoot, it's just like too much, you know? I'm really giving you so different, beautiful numbers. Questions. Secant of x minus tangent of x. Okay. What do we do first? We substitute pi over 2. We know that secant, what's secant? That's 1 over cosine of x. Yep. Because I'm not really good in working with seconds. I know really good cosine of sine. Sine and cosine, this is just like strong side. I'm not really good with tangents either. I know sine, I know cosine, I know that tangent is sine over cosine. I know secant is 1 over cosine. So this way I can, sometimes think about the values of those functions. So imagine we substitute pi over 2 to secant. So secant is 1 over cosine of x. We substitute pi over 2. So we get 1 over cosine of pi over 2. So we get 1 over 0. 100% this is undefined. And the same thing will happen with tangent, because tangent is sine of x divided by cosine of x. And if we substitute now pi over 2, you will get the same cosine of pi over 2 at the bottom, which is, again, 0. And we can't have 0 in the denominator, we know that. So the substitution doesn't work, unfortunately. And we need to do something else. Okay. And here, as you know, it's not going to be the L'Hopital's rule, as you see. It's some 1 over 0 minus 1 over, it's not even 1, it's some, yeah, it's going to be 1 over 0 minus 1 over 0. So some strange things are happening. Really strange things are happening. And we need to do something with that. And basically, let's write it down. Let's just rewrite it this way, and we'll start working. Because trigonometry, as you know, trigonometry is also a huge part of math where you have a bunch of formulas, and you can apply them too in order to get the final answer. So we will try to do that. Sine of x divided by cosine of x. And basically means that we can write it down as the limit as x approaches pi over 2, from the left by the word, of 1 minus sine of x divided by cosine of x. Good. What do you do next? Now this is a very good question. What do you do next? Let me think. But at least in this form, if you substitute pi over 2, oh yeah, at least now look at the form. Now we can write, when we write it down this way, 1 minus sine of x divided by cosine of x, and you substitute pi over 2, we get 1 minus 1 divided by 0. So we get the indeterminate form 0 over 0, basic form. And what do we do now? We can apply the L'Hopital's rule now. When you kind of change the expression, you rearranged the expression, you kind of change it a bit, some trick, right? But now we can apply the L'Hopital's rule. Before you couldn't, because it had 1 over 0 minus 1 over 0, some weird stuff. We can apply the L'Hopital's rule only when you have 0 over 0 or infinity or infinity. Oh, again, this is for AP Calc course. Only in these cases. And now we can apply the L'Hopital's rule. Just fine. Of course, there's also a different method actually. Just to finish this stuff with trigonometry. But okay, let's do L'Hopital's rule. Let's apply that stuff. And we need to take derivatives, that will be sine of x. And here we'll get negative cosine of x. Yeah. Or not, yeah. Of course, we don't forget about the limit. This is a basic problem. And we get, and now if we substitute pi over 2, we will get negative. So we'll get 0 divided by 1. So it's 0. Answer is C. Let f be a function such that limit of f of x as x approaches 4 is 7. Which of the following must be true? F of 4 is 7. Not for 100% actually. It's even about it's more about continuity actually, not even about limits, but okay, let's say that. What's the definition if you say that f of x is continuous? At some point C, when we say that f of x is continuous at point C, it means that what? If we say that it's continuous at point C, it means three important things. First, it means that f of C exists. Second, it means that limit as x approaches C of f of x exists. And third, it means that limit as x approaches c of f of x is equal to f of c. So this, this is real definition. In simple words, graphically, it means that you can sketch it without lifting up your pencil. Yeah, but this is continuity on the entire interval. But at the point, it just means graphically you have no jumps, holes, or asymptotes. But definition, strong definition, analytical definition is that your function is defined there. First, f of c. Second, the limit exists. From the left and from the right, you approach the same value. And third, the limit is equal to f of c. In this case, your function is continuous. All right, and what do we know from the fact that limit exists? So basically, they just say that you have a function f, and the limit exists of f of x as x approaches 4, and it's equal to 7. Which of the following must be true? And basically, the only thing you know that the limit exists. You don't know about function at all. It doesn't, your limit and f of c, they're not connected, basically. You don't know whether your function is continuous. You don't know that. You only know that your limit exists. Basically, the only thing you know that left-hand limit and right-hand limit and left-hand limit are equal to each other. You know that one side limits are equal. This is the only thing you can actually know. They're equal to 7. They're equal to each other and equal to 7. This is the only thing you can know from the fact that limit exists. You don't know about the continuity. Because first, f of 4 equals 7. We don't know. We don't actually know. Because limit doesn't care whether your function exists or not. We don't know that. B, f is continuous. We don't know because I don't know a thing about f of c. And I don't know whether f of x is equal to f of c. I don't know that. C, absolutely, this is true. This is the only thing I know for sure. I know that left-hand limit is equal to 7. And it's equal to a right-hand limit, which is also 7. And that's why general limit exists in 7. This is the only thing we know. And D, f is defined as 4, of course not true. So C is the only true thing here. True answer. Alright, number 13. Wonderful. So we already discussed, and this is the place where you need to use the rational theorem. You need to look at the denominator, and the numerator, of course, too. You need to look at the numerator, and you need to identify the x with the greatest exponent. Here it's x cubed, and you say, okay, the degree of the polynomial in the denominator is 3. We have 3 here. In the numerator, it's 4. 2x to the 4th. This is the highest exponent. So, numerator loses, right? This fight. And it means that you have something bigger, something greater. And it means due to the rational theorem, you will get 0. If you don't, because the degree in the numerator is higher. Again, if you kind of don't remember, you think, oh, does it mean that it's going to be infinity or 0? You don't remember 100%. You have to apply my logic. You say, okay, let me look at the expression. You say, okay, x cubed is much bigger than anything else. Forget about it. Let's just forget about it. The same thing here. 2x to the 4th is much greater than anything else. I don't care. So I can write it down. This is what happens. This is what's happening in your head. You say, okay, this is x cubed divided by 2x to the 4th. And now you can just cancel out x cubed, and you get it's going to be limit as x approaches infinity of 1 over 2x. What's that? It's 1 divided by infinity. That's going to be 0. So this way you can easily check yourself. And as I promised, let's also show the third method. Because we actually, we don't just learn to evaluate limits. We also try to get the logic around different methods, different tricks and tips, and so all that stuff. And third way, a different way to approach this problem is to use the trick called divide the entire expression by divide numerator and denominator by the x with the highest exponent in the entire expression. So again, we can write it down. It was actually a mistake too. erase that. Okay, 2x to the fourth plus x squared plus 3x plus 2. And a different approach, right? You look at the expression and now you find the x with the highest exponent in the entire expression. We see, okay, 2x cubed. This is x cubed, right? 4. This is like the highest exponent here. This is the dude. This is the g. And then you say, okay, let me divide both numerator and denominator by x cubed, x to the fourth now. So you can write it down this way. X cubed divided by x to the fourth. Okay, let's write down first this way. Oh, you know, I'll be smarter. I'll be smarter this time. I'll just take it. Copy. Woo! And we divide it by x to the fourth. So we divide both numerator and denominator by x with the highest exponent. And we can do it because basically we divide by 1, multiply by 1. Now again, basically we just multiply by 1, so nothing changes because of course we can do that. It's again some trick. X to the fourth. Wonderful, and now let's rewrite it this way. I don't have enough place. Yeah, let's write down this here. So it's going to x approaches infinity of x cubed divided by x to the fourth plus 2x squared divided by x cubed, x to the fourth minus 7x divided by x to the fourth plus 4 divided by x to the fourth divided by 2x to the fourth divided by x to the fourth plus x squared divided by x to the fourth. Of course, it's kind of long to write it down. You might think, why would on this earth I do that? Ever, because it kind of takes a bunch of time, but it's just you can actually do it in your head because you don't need to write all that stuff. I'm just showing it to you. So look at that. What happens here? We basically know that we can cancel out now everywhere x's, something like that. So it will be x to x squared, be just x cubed, and so on. You understand? Basically, we'll get only two types of different terms. We'll get something like 1 over x squared or 1 over x cubed, right after we cancel out everything, or maybe 1 over x. And they're all, if we substitute infinity then later, they're all, what do? They approach 0, right? They equal to 0 as x approaches infinity. As we substitute infinity, we'll get 0 in every term. And so this is going to be 0, 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 this is going to be 0. And another type is something like 2x to the fourth divided by x to the fourth. And here you just cancel out x to the fourth and you get just 2. So you get a bunch of zeros, 0, 0, 0, 4 zeros in the numerator, so it's going to be 0 in the numerator, divided by 2 plus zeros. So the final answer is going to be 0. That's all. So this way you can also tackle this problem and get the correct answer A. One more break. Alright, I'm here, so let's continue our conversation finally. Alright, the graph of a function f has vertical asymptote at point 2. Which of the following statements must be true? And again, it's kind of bit limits and the continuity anyway. So, what is vertical asymptote? Basically, what's going on? Oh yeah, now it's fine. Vertical asymptote basically means you have some line, vertical line at vertical asymptote at point C, let's say, means that there's a vertical line C that is never crossed by your function, the graph of your function. Okay, this is what it means. And basically, it just means that it's C. I mean, it just, oh, what's going on there? Yeah, it doesn't necessarily mean that your function the limit of a function is infinity. It's not that. I mean, it can approach infinity only from the left, and from the right it can approach negative infinity, for example, or just be these, something like that. So it should approach at least from some side, from the left or from the right, or from the left or from the right. Yeah, it should approach infinity. It should tend to, so it should grow without any boundary as x approaches c from the right or from the left. So that's why c is true. But it's not necessarily true that the general limit should be equal to infinity. I mean, there are cases where it's true, but sometimes it's not true. A perfect example is 1 over x, function 1 over x. So this is the graph for a function. So at point 0, for example, at point 0, the limit as x approaches 0 doesn't exist of x. But from the left, because from the left we approach negative infinity, from the right we approach positive infinity. Oh, from the left we approach positive infinity, from the right we approach negative infinity. What's that? Yeah, negative infinity. So the general limit doesn't exist here at all. So it's not equal to infinity. Limit as x approaches 0 of f of x is not equal to infinity. It doesn't exist in a finite sense and in an infinite sense too. It doesn't exist just in any senses. But from the left, yeah, the limit from the left is equal to infinity. From the right, negative infinity. But the situation will change if we put here squared. For example, imagine now function is f of x divided by 1. Now let's do it this way. Imagine now if f of x is equal to 1 over x squared. Then this way, you'll have now the situation where left-hand limit from the left as x approaches 0 from the left, the values of a function grow without any boundary. And from the right, the same thing. So yeah, we'll see that generally infinite limit exists and equal to infinity, right? We like grow without any boundary. That's why the answer is C. B is not guaranteed. Sometimes it can be true. Like here, yeah, it's true for f of x, which is 1 over x squared. But for 1 over x, it's not true. But C is true always. At least from the left or from the right, we approach infinity. We grow without any boundary. Without that, there wouldn't be any vertical asymptote there. Vertical asymptote is the line that shows that our functions grow without any boundary and never crosses this vertical line. Never. It just goes and goes and goes somewhere to the top, to the moon. It flies to the moon. All right, number 15. Let's switch to red. Why not? And here's the trick. Of course, now you can substitute 0. You'll get 9 minus 9 divided by 0, so which is 0 over 0 one more time. Doesn't work. Let's write it down. 0 over 0. So, doesn't work. And, of course, you can evaluate this limit using all the other rules we discussed previously. You can do L'Hopital rule. You can try to factor, maybe do something here. Try to simplify. Yeah, it will work. It will work. All the other methods will work too. But let me give you one more trick. When you look at that, you might realize what? But it kind of looks like the derivative, the definition of the derivative. It really looks like that. I mean, if you remember, this is the definition of the derivative at point A. F of x plus A minus f of A divided by sorry, A plus H. We'll write down with H, right? F of A plus H minus f of A divided by H. So this is the definition of the derivative. And look at that. I mean, do you see that they're kind of similar? And we can see that our function, it seems that f of A here is what? Oh no, or I'm not right. Let me think a bit. Oh, wait a bit. Subject 3. Oh no, exactly. We see that it looks like that our function is x squared. F of x here is x squared, and if you substitute a, you see that's going to be not a 3. In this case 3. You'll see that's going to be 3 squared, right? We see that. And if you substitute 3 plus h, f of 3 plus h, it's going to be 3 plus h squared. So we can see that this is just exactly the definition of f prime of a, where not a 3, f prime of 3, where f, our function, is x squared. F of x is x squared. Here, of course, it's not super, logical to use that, but sometimes your functions can be really difficult. Or you might see that there's a bunch of L'Hopital's rule to apply. Yeah, sometimes you can see sines or cosines, and identifying the definition of the derivative can be really useful. And here, look at that. Now I see, yeah, it's x squared, so the function is x squared, and this is the basic definition of the function x of our derivative of our function at point 3. So we can just find the derivative, f prime. We find the f prime of x is going to be 2x, and we need to evaluate at point 3. That will be 6. So the final answer is 6. That's all. Of course, we can solve it applying all the other methods. No. If you want, yeah, try to, again, pause the video, try to solve this problem yourself, try to use the tricks we discussed previously, or some of them, and get the answer. But I'm sure you'll get the same answer. But this is some kind of shortcut, especially if you can look at that and recognize that, yeah, it looks like some definition of the derivative of some function. And here you recognize the function is x squared, that the function is x squared. All right, number 16. If f of x is equal to sine over x, sine of x divided by x, and 1 when x is not 0. 1 when x is 0, and sine of x divided by x when x is not 0. Then f is, let's go one by one. This continues at point 0 because limit doesn't exist. Let's see. Basically, we just need to look, in order to, as we see, there's everywhere there's some limit as x approaches 0 of f of x. And we have to make sure that it exists or doesn't exist. Let's see. How do we do that? We need to look at the limit from the left and from the right. From the left, it means that, of course, x is not equal to 0. Right? So we take this function. And it means that the limit as x approaches 0 from the left will be the limit of sine of x divided by x. What's that? This is the basic trigonometric limit. And we know that it's going to be 1. Or you take the L'Hopital's rule, right? Again, you substitute 0, you get 0 over 0. You apply the L'Hopital's rule, and you'll get cosine of x divided by 1, which will give you 1 eventually. So it's 1. From the right, the same thing. From the right is going to be the limit as x approaches 0 from the right. Again, we take sine of x over x because we're not equal to 0, right? We come close to 0, but we're not 0 exactly. We're from the right, and we take values close to 0, but greater than 0, and less than 0. But it's going to be sine of x over x. We'll have to use this function. So it's going to be 1 more time. So from the left and from the right, we approach the same value. So the limit exists. This is for 100%. It basically, if you talk about continuity at point 0, because as we see, there's also, basically it's just about, is it continuous, is it discontinuous, does the limit exist or doesn't exist? We need to just look at these two things. We need to identify whether limit exists and whether function is continuous. Two things. First of all, we see that limit exists. Second, now if we see that f of c exists, f of 0 exists, and we show that limit as x approaches 0 is equal to f of 0. If we show that, and we know that f of 0 exists, sorry, some lags, it means, yeah, sorry, let me move a bit here. The first fact, of course, we know that f of 0 exists, right? We can look at the function. It's given that it's 1. F of 0 is 1. Its existence equal to 1. And it's basically the first condition of the continuity. Second is already proven. The limit exists. And it's equal to 1. We already proved that. And it's basically also means that the third condition is also done. Because it's equal to f of 0. Exactly. It's 1. So it's continuous. That's why C is true. This is the final answer. We move forward. 17. Let's smash this limit. X squared plus 3x square root of x squared plus 3x minus x. Ooh. Yeah, if we substitute infinity, we'll get some infinities minus infinity. And it means that we can't use L'Hopital's rule. Because we need the form where we have a fraction, f of x and g of x, as you remember. We need to somehow change it, transform it into this form. And let's at least, anyway, try, first of all, to multiply by conjugate and divide by conjugate. I'm sure it will help. And at least it will transform that into L'Hopital's rule usable form. So that will be x squared plus 3x minus x divided by x squared plus 3x plus x. And here, again, x squared. Square root of x squared plus 3x minus x. Yeah, and basically we can write it down as the limit, as x approaches infinity, of x squared plus 3x plus x squared. No. Yes. Here's plus. Negative. Negative x squared. Sorry, it's been a mistake. Divide by this weird thing. So basically get the limit as x approaches infinity of 3x divided by this ugly thing. Alright, what do we do now? Now we substitute infinity and we'll get infinity over some infinities. So finally, we can apply L'Hopital's rule in this form. Because we get to a point where, yeah, we can apply L'Hopital's rule, and let's do it. Now we take the derivative. So from the top, that will be 3 as x approaches infinity. We move to the bottom. We take the derivative here. It's gonna be, it's gonna be 1/2 multiplied by x squared plus 3x to the negative 1/2 multiplied by the derivative of the inside, which is 2x plus 3, and that's all plus 1. So we get some really, really, really dirty thing. Let's remove that from the top. I need some place here. So sorry. Yes, and so we can write it down this way. It will be 3 divided by 2x plus 3 divided by 2 square root of x squared plus 3x. So we have some weirdo in the denominator. 3x, yeah. So this is it. Now if we substitute, we applied our L'Hopital's rule. Now we actually get to a point where if we substitute infinity, we get 3 divided by, again, some infinity or infinity. It didn't really help. Plus 1. I mean, it kind of helped, but we still don't know how to deal with this thing. And the key here is very simple, in fact. I mean, you can just work with this. And that's why actually remember the trick we used previously with rational theorem. That will be really useful here. basically nothing I'm saying here is unuseful. Everything is extremely useful. So we look at that. We need to somehow figure out what is this as x approaches infinity. And in order to do that, let's apply the trick we actually did previously. Let's divide by x. Let's identify the x with the greatest exponent. But I mean, you know, it's not x squared because there's also squared. It's hard to explain, but if we divide by x here, I mean, it's actually not super simple limit. But if we divide by x here, both numerator and denominator, so basically we'll write it down this way. Again, now nothing changes, in fact. We write it down this way. And then we'll bring this x inside. What do we get here? And so let's rewrite it this way. It will be 2 plus 3 over x divided by 2. And inside, we bring x inside. That will be 1 plus 3 over x. Basically, we did nothing. Nothing has changed. But now, as you see, if we rewrite this limit this way now, we rewrite it as 3 divided by 2 plus 3 over x divided by 2. Let me remove that. 2. Sorry. 2, 1 plus 3 over x. Now, if we write it this way, and we substitute infinity plus 1, what happens now? We see that that's going to be 0, that's going to be 0, and that will be just 2 divided by 2 here, so it's going to be 1 plus 1, and 3 divided by 2. The final answer is going to be 3 over 2. You know, everything's going to simplify. Just because you decided to rewrite the expression in a different manner, like in a different way. So decide that maybe let's divide both by x, and it works, and then it helps. Yep. All right, let's move faster, right? Let's finish all that stuff. Number 18, let f be a function defined as f of x minus 3 over x minus 3. The absolute of x minus 3 divided by x minus 3. What is the limit as x approaches 3? And the basic, you know, when you work with some absolute value functions, just rewrite it as a piecewise function. It's just easier. So understand that it's going to be x less than 3, let's say, and x greater than 3. Let's say greater than or equal to 3. Don't care. In this case, that will be what? That will be negative 1. In this case, it will be 1. Right? Because, let's rewrite it actually. Oh, sorry. Okay. So it will be x minus 3 divided by x minus 3. So here with minus. If x less than 3. And it will be x plus minus 3 divided by x minus 3 for all x greater than or equal to 3. And basically that just means that f of x is equal to negative 1 for all x less than 3, or 1 for all x equal to greater than 3. That's all. And now, what is the limit as x approaches 3? And basically, as I told you, when you look at the piecewise function, you have to, first of all, ask yourself a question. Does the limit exist? And here, it's not going to exist. And let's prove that. They're very simple. We need to look at the left-hand limit. So from the left, as we approach 3s from the left, the limit of f of x is going to be negative 1, right? This is going to be just number. The limit of the number is just number. From the right, as x approaches 3 from the right, that will be 1. So the left-hand limit is not equal to right-hand limit, so one-side limits are not equal. General limit doesn't exist. So the answer is doesn't exist. And graphically, too, you know, if you just sketch it graphically, it would be really easy to, I mean, versus some point 3, let's say, and all right, let's say 3 is here. So for all x less than 3, it's like that. it's 1 and negative 1. Right? So there's some jump. There's some discontinuity there. It's discontinuous there. All right, number 19. And we have to evaluate this limit. And we see that that will be easy go L'Hopital rule. I'm sure. We apply 2, okay, maybe even 1 time. Of course, first we substitute 0, we get 1 minus 1 over 0, which is going to be 0 over 0. We move forward. Now we prove that we can use L'Hopital's rule, so let's do it. We have f of x, we have g of x. Let's take the derivative of f of x. That will be 1 minus sine of negative sine of 2x. So it will be plus sine of 2x multiplied by 2. Derivative of the inside. Derivative of 2x is 2. Divide by derivative of 2x, which is 2x. Now, very simple. Or maybe not. If substitute 0, we'll get... Wait a minute. What's going on here? That's actually a good question. If substitute 0, if substitute 0, we get 1 plus sine of what? Sine of 0, which is 0. So we get 1 divided by 0. It's really strange stuff. Really strange. Ah, and I forgot the limit. Sorry. So we substitute 0, we get 1 plus sine of 0 multiplied by 2, which is 0. Yes or not? Yes. So we get 1 divided by 0, and it means that we can't use L'Hopital rule anymore. So we need to work with this thing now. That's sad. That's pretty sad, actually. Oh, wait a bit again. We take the derivative of cosine of 2x. That will be sine of 2x, negative sine of 2x, multiplied by 2. Yep. Strange. It's strange, but okay. It's really weird. What happens now? What happens now? What do we do now? This is a good question. We need to do something else because we substitute 0, we get 1 over 0. Which is a really weird thing. 1 plus 2 multiplied by 0. Now, what do we do? What is the next step? Let me think about it. What can we do now? We need to make some trick again. It's really strange. It seems I'm getting stupid. It seems I'm getting really stupid now. Let's take a pause. Oh, sorry. Of course. Yeah, I'm maybe I'm already tired a bit. Sorry. Of course, the derivative of 1 is 0. I've just decided to keep the 0 here. Yeah, that was my stupid mistake. Sorry, very sorry. I was thinking, what's that? It was really weird situation. And now we divide by 2. And we get that limit as x approaches 0 is equal to sine of 2x divided by what? Divided by x. And as we remember, we already tackled a similar limit. We know that it's going to be 2. You either do it as a basic random limit or you apply L'Hopital's rule one more time. Let's do L'Hopital's rule, okay, one more time. We know that because if we substitute 0, we'll get 0 over 0. So we can apply L'Hopital's rule. That will be, we take the derivatives one more time. That will be cosine 2 cosine of 2x divided by 1. So when we substitute 0, we get 2. So the final answer is 2. Alright, finally, the last one. Oh, thanks God, so easy. Oh, it seems like we did it, right? We did it before. We did it! And we know that the final answer is going to be 4 over 5. But let's just remind ourselves a bit. What do? We know that this is the rational theorem. We identify the x with the greatest exponent in the numerator. That's going to be 4x cubed, x cubed. So the degree of the polynomial in the numerator is going to be 3. The degree of the polynomial in the denominator is going to be 3 too. So we receive the highest x with the highest exponent is also 3. So it's x cubed. And then it's going to be the ratio of the leading coefficients. So it'll be 4 over 5. Or we can also remember that, right, in this case, we can say that it's approximately limit as x approaches infinity of 4x cubed divided by 5x cubed, because anything else, it's not important, absolutely super small. And then we can cancel out x cubed, that will be 4 over 5. But again, I beg you, don't write down this way. It's just how you have to check yourself. Okay, this way you can easily check yourself. So yes, I hope that was really useful. I'm almost sure we tackled all the different types of limits. And this is all. Remember, first of all, you do the derivative substitution. This is first thing. Then you apply different rules, methods, tricks. You can try to factor. Maybe you can remember some trigonometric formulas or something. But really, the ultimate weapon, the main hero here is L'Hopital's rule, because usually when you get the indeterminate form, you need to apply the L'Hopital's rule. But even if you can't, you have to just transform your expression to a form where you can apply it, and that will be all. And that will be all. Sometimes, yeah, you can use the derivative definition. Sometimes you can do some algebra tricks, and that will be even faster than L'Hopital's rule, right? It depends. It depends on the situation. It depends on the scenario. Rational theorem, we already just discussed that. And Squeeze Theorem. That's basically all about limits in AP Calculus, both AB and BC. But it's kind of all for most of Calc students. Of course, if you take some really complicated Calc course, it's a bit different, 100%. But for most of the students, that's fine, just fine. I hope that was a useful, great lesson. See you soon. If you want to see a part 2 about the derivatives, right? If you want to move forward, smash the derivatives, then integrals, all that stuff, relate the race problem, we'll just do this series and we continue. And with me, we will smash these exams. We smash AP exam. If you want to just cover the entire course, everything completely finished inside in one course, I was sitting and making those videos for every lesson from the College Board plan. I was tackling every lesson, of course, in further detail and everything. And plus, I was also doing unit smash times, where I was tackling all the problems, all the possible problems. I mean, you will have all that stuff inside of the course on smashap.com. And plus, you will also get an access to community. So basically, you get a bunch of things. And if you want to get all that stuff and cover the entire AP Calculus course for $99 with me, of course, I was the man who created the course. You will be in touch with me. You will be in community with me and so on. Then go to smashap.com and enroll in my AP Calc, AB, and BC courses. But yeah, generally, that's all for today. See you soon. I'm waiting for your comments.